Imagine drifting alone in the vast emptiness of deep space. You throw a rock as hard as you can, expecting it to keep flying in a straight line forever, just as Newton's first law predicts. But instead, something strange happens. The rock slows down and eventually stops. Where did all its energy go? This question troubled some of the greatest minds over a century ago, including Albert Einstein himself, and it leads us to a profound gap in our understanding of the universe. At the dawn of the 20th century, physicists were wrestling with the principle of energy conservation, a cornerstone of classical physics that seemed to falter in the new realm of relativity. Einstein's groundbreaking theory of general relativity redefined gravity as the curvature of space-time, but it posed a troubling puzzle. Could energy truly be conserved in such a curved and dynamic universe? Einstein thought he had a solution, proposing that if you combine the energy of matter with that of the gravitational field, the total should remain constant. Yet his solution contained a subtle flaw that only a remarkable mathematician named Emmy Noether would uncover, and her insight would revolutionize physics forever. In 1915, Einstein lectured at the University of Göttingen, presenting what would become the general theory of relativity. The equations he unveiled were revolutionary but still incomplete, especially regarding energy conservation. Legendary mathematician David Hilbert, intrigued by Einstein's work, tried to find energy conservation laws within the new theory, but only stumbled upon the Bianchi identities, which implied energy conservation only in a perfectly empty universe, a universe unlike our own. Hilbert turned to his brilliant assistant Emmy Noether, who, despite facing severe gender discrimination, had already established herself as a leading expert on symmetry in mathematics. Her journey was extraordinary. Barred from official university enrollment simply because she was a woman, she persevered through sheer talent and determination, gaining special permissions and absorbing cutting-edge ideas on symmetry and geometry. Symmetry, though simple to observe, like the mirrored halves of a triangle, is far deeper and more abstract in mathematics and physics. Noether generalized symmetry beyond shapes to include transformations that leave certain properties unchanged, even in complex systems like mathematical functions or the laws of physics themselves. Over 12 years, she honed this expertise to confront one of the most profound puzzles in science. Einstein's proposed energy conservation equation relied on a mathematical construct called a pseudo-tensor, which failed to behave properly under changes of reference frames. Noether realized that Einstein's approach violated the fundamental principle that the laws of physics should look the same in every frame of reference, a principle called general covariance. If this principle held true, the usual notion of energy conservation might not apply as previously thought. This led Noether to an astonishing conclusion: the deep connection between symmetries and conservation laws. She proved that every continuous symmetry of nature corresponds to a conserved quantity. For example, the symmetry of space under translation guarantees conservation of momentum. Rotational symmetry ensures angular momentum conservation. And crucially, symmetry of time, meaning the laws of physics don't change over time, leads to conservation of energy. This is now known as Noether's Theorem, a foundational pillar that explains why conservation laws exist in the first place. But our universe isn't static or empty. Observations in the 1920s revealed that distant galaxies are speeding away from us, proving the universe is expanding. Later, in the 1990s, astronomers found that this expansion is accelerating, meaning the universe's structure changes over time. This breaks the symmetry of time, which in turn means energy, as we typically understand it, is not conserved across cosmic timescales. Take, for example, a photon of light emitted shortly after the Big Bang. As it journeys through the expanding universe, it loses energy, stretching from visible light to microwave radiation. Where does this energy go? The honest answer is that it doesn't go anywhere. Energy conservation doesn't hold in the way we expect. And this isn't a violation of physics, but a natural consequence of the universe's changing nature. This explains why the astronaut's rock in space slows and stops. Its energy dissipates not into some mysterious sink, but rather the concept of energy conservation itself becomes murky without the time symmetry we take for granted on everyday scales. Yet Noether's insights did not just stop there. She also showed that in general relativity, where space-time is curved and dynamic, global symmetries, like those in empty space, no longer hold. Instead, only local symmetries, those that apply in infinitesimally small regions, remain valid. From these local symmetries arise continuity equations rather than strict conservation laws. Imagine water flowing through a pipe. Locally, water volume is conserved, but if the pipe has leaks, water can escape. Similarly, energy in space-time can leak through the curvature, preventing a simple global conservation law. Einstein's dream of a neatly conserved energy law within his theory had to yield to this more complex reality. The universe's expansion, curvature, and evolving nature mean energy conservation is more nuanced and limited than once believed. Noether's work reveals that conservation laws emerge only when certain symmetries exist. And when those symmetries break, so do the strict conservation laws. So why does energy seem conserved in our daily life? Because over short timescales and small regions, the universe's expansion is negligible. The laws of physics appear time invariant, and energy conservation holds approximately. But on cosmic scales, spanning billions of years, the universe's accelerating expansion breaks this symmetry, and energy conservation no longer applies in the traditional sense. This profound realization reshapes how we think about fundamental physics, gravity, and the cosmos. It invites us to embrace a universe more fluid and dynamic than Newton's rock, where even foundational laws bend to the fabric of space-time